Welcome back. In this video, we continue with the electronic structure of molecules, and now we look at constructing term symbols for labeling molecular electronic states. And we're going to do this with an approach similar to what we did for term symbols for atomic electronic states, in the sense that we used operators that commuted with the Hamiltonian. We took their quantum numbers and used those quantum numbers to define the term symbol. So we're going to do something similar in the case with molecular electronic states. Now we're going to focus on linear molecules in this video and in this course because we don't cover group theory, and you need group theory to really do the term symbols for nonlinear molecules. But the ideas that we do here can be useful when you get to designing term symbols for nonlinear molecules. Now we're also going to assume that we're working with cases where there's small spin orbit coupling, so we're looking at molecules with low Z atoms involved. But in this case, then one operator that commutes with the Hamiltonian is the LZ, which is this is the Z component of the orbital angular momentum, which is along the bond axis. So the bond axis is defined to be the Z axis, and so the LZ, which is the Z component of the orbital angular momentum, commutes with the Hamiltonian. L, the total orbital angular momentum, doesn't commute, but the LZ component does commute. So its quantum numbers are going to be good, and so this M sub L times H bar, which is its eigenvalue, has these quantum numbers M sub L, capital M sub L, which has values of 0, plus or minus 1, plus or minus 2, and so on. Now we can get this M sub L by adding up the quantum numbers associated with each of the electrons' orbitals. So remember when we talked about the molecular hydrogen cations quantum numbers, one of those quantum numbers was this M quantum number, which was associated with symmetry about the bond axis. And if we take those M values and we add them up, we'll get capital M sub L. And we also learned that the states with plus or minus M sub L are degenerate in energy. So we're going to just simply label our states by the absolute value of M, which we're going to use this symbol capital lambda here. And so states with different lambdas will have different energies. So based on that lambda value, which is the absolute value of the capital M sub L, we will assign letters to our term, which are either sigma, pi, delta, phi, or gamma. These are uppercase Greek letters, similar to what we did with atomic states with capital S, P, D, F, and so on. And those are going to be assigned based on the quantum numbers for the total angular momentum, orbital angular momentum along the bond axis, this LZ operator. Similarly, the total electron spin angular momentum operator does commute with the Hamiltonian, and so we're going to be using the spin multiplicity just like we did with the atomic term symbols, and we're going to need to get the M sub S values by adding up the individual M sub S values for all the electrons in the individual molecular orbitals. So we'll add them all up to get the total M sub S value. And then additionally, we'll have a total angular momentum along the bond axis, which will be the contribution from orbital plus spin angular momentum. So that will be given by this lambda plus capital M sub S, and that quantum number, which it's the eigenvalue is that times H bar, but lambda plus M sub S is the quantum number that we will put down here as a subscript for labeling our term. So this is how we're going to label our term. From these two quantum numbers, we'll use the lambda letter here, the spin multiplicity, and then this total angular momentum component along the internuclear axis. Now there are other operators that commute with the Hamiltonian that will be helpful to add those to the term symbol, but they are for certain specific cases. So when you have the sigma state, it turns out that the mirror operator applied across the XZ plane. So the Z axis, remember, that's what is the internuclear bond axis. So the XZ plane, if you do a mirror of that and you look at the wave function's behavior, so if the wave function changes sign, then it has an eigenvalue of +1. If it changes sign, if it stays the same sign, it's +1. If it changes sign, it has eigenvalue of -1. So these two eigenvalues, plus or minus, we will actually add to the term symbol as a superscript to the right to indicate its quantum numbers under this operator. For homonuclear diatomic molecules, we'll also be interested in the quantum numbers for the parity operator, which commutes with the Hamiltonian in this case. So, and we've already done this already. We talked about the G and U symmetries, which is the symmetry of the molecular orbital under the parity operator, but for the total electronic wave function, we'll have the eigenvalues for this parity operator, and those will be either plus or minus 1, but we can get that from the individual molecular orbitals that are occupied in the total multi-electron molecule. So if you take the individual molecular orbitals and if you take the product of all of them, so for example, if you have 2 electrons in molecular orbitals, then you just look at their G or U symmetries and you just multiply them. So if you have 2 with 2 G's or 2 U's, then you're going to end up with a G. If you have 1 and a G and 1 and a U, or 1 and a U and 1 and a G, you're going to end up with a U here. So this is how our symmetries will work out, and this will be another subscript that we'll put, or actually we're going to put this as a subscript to the right, so it might actually, when we'll have to remove this one to place this G or U when we're talking about homonuclear diatomic molecules. When we're talking about heteronuclear molecules, then this parity operator is doesn't commute with the Hamiltonian, so we won't have that extra term, a symbol in our term. So let's look at an example here. This is the boron diatomic molecule. Here is the MO electron configuration that we would get. And so you can see we've placed all the electrons in, and we have the highest occupied or orbital here, the HOMO, with the 2 electrons in it. And these closed shell electrons aren't going to contribute, because if you add up all their M sub S and M sub L values, they all add up to 0. So it's only these 2 here that we have to focus on. So if we go over to making ourselves a table, kind of like what we did with the atomic term symbols, except now we know that these electrons can go into molecular orbitals that are either M of plus or minus 1 and M sub S of plus or minus half. So given that we have Pauli's exclusion principle, there are 6 possible ways in which we can arrange that. So again, this is not too dissimilar to what we did with atomic states. In fact, it's probably a little easier. So let's take a look at how we might then figure out and what are the possible terms that are associated with the B2 molecule with this particular electron configuration. So we're going to fill out the total M sub L, which we're just going to get by adding together the M values for each of the orbitals that are occupied, and then the M sub S value from the spin state of each of those. So I'll put those in here, and here are the values, and here's the terms that we're going to work through here in a bit. But here are the values that we get for each one of these configurations there. Now, the first thing is that this is a homonuclear diatomic molecule, and each of the electrons, go back here, is in a orbital with U symmetry, or here you see with U symmetry. So that means that for electrons in U symmetry, the overall wave function is going to have G symmetry. So all of our terms are going to have a subscript G on them. Now, let's get to the M sub L values. Well, we see in the M sub L values that there are, most of them are 0, except for these 2, which are plus or minus 2. So with M sub L, with values of plus or minus 2, that would correspond to a lambda of 2, and that only occurs with M sub S values of 0. So that means that we have a lambda of 2 case associated with an S of 0 case. So with lambda of 2, we are going to pick the delta for the symbol. With S of 0, we have a spin multiplicity, that's 2S plus 1, so that's going to be a singlet. And since we've already decided it's G, then we know that that's going to be a singlet delta G. So that is going to be associated with these 2 states. Okay, let's move on. We've assigned 2 of them. We have 4 left. Of the 4, they all have 0 for M sub L, but we see that 3 of them have states that could be associated with S equals 1. So if we have M sub S of 1, 0, and minus 1, that would correspond to an S of 1. So we can then say that we have one state which has, we have 3 of these configurations with lambda equal to 0 associated with m sub s of -1, 0, and +1. So that means we have this s equals 1 state. So with lambda equal to 0, we have a sigma state. With s equal to 1, we have a triplet. So the multiplicity is 3, and again, it's G, so we're going to label this 3 triplet sigma G. So that means that these states that all have m sub L 0, that we're going to be able to assign that those are possibly associated with the triplet sigma G. So that leaves us with just 1, so we've assigned 2 here, 3 here, and now we have 1 left, and that's the one associated with capital lambda of 0, and there's an s of 0 because there's only an m sub s of 0, so that means that the total s is 0, so that means we have left over a singlet sigma G state, and that would be either one of these 2 here. So now we've identified the 3 possible terms you can have for the B2 molecule, which is the triplet sigma G, the singlet delta G, and the singlet sigma G. All right? So we can also follow, just like we did with atomic terms, so Hund's rule to determine which one is the lowest energy term. So in Hund's rule, we knew that the term with the highest spin multiplicity was the lowest in energy. So if you look at these, the ones with the highest spin multiplicity is going to be the triplet sigma G. So we'll assign that one as the ground state for the B2 molecule. Now, the other 2 terms will be, the next highest one will be the singlet delta G, and then the highest one will be the singlet sigma G. All right, I think that's it for this. In the next video, we'll look at identical nuclei and molecules.